This really includes anything from key management services to nodes to wallets, basically anything that interacts with blockchains are responsible for
Works
securing
for
funds.
CoinBase.
Just a quick overview of what we're going to be covering today. We're going to start with some metrics and sort of the current state of Coinbase's e-staking program, and we'll dive into the threat model to understand how and why someone might want to attack this infrastructure. It's going to cover some key management principles, our SSDLC, or secure software development lifecycle, cover some infrastructure security controls, and then talk about our forward vision and how we're externalizing some of this work to customers and communities away. So here's kind of the current state of our e-staking infrastructure. We're currently operating roughly 139,000 validators, which is about 11.5% of the network. This equates to about 4.4 million e-staked and an estimated value around 17 billion, with 0 slashing events to date, which hopefully speaks to some of the great work that our product teams have been doing to build a reliable infrastructure. So move on to the threat model. In order to understand how to protect such a complex system, you first want to understand how and why someone might attack it. So let's go into some of the various attack scenarios, and we'll use that to inform our analysis on how we implement protections for them. So the first and foremost attacker goal would be stealing the withdrawal address, private keys associated with our withdrawal addresses used by our validators. So anyone that holds the private key to this withdrawal address is ultimately the owner of any sort of stake principal. And so we really want to make sure that we are protecting that. As with the recent Vector upgrade, the holder of that private key is able to initiate a unstake request for all the validators that are using that address. And then they would be able to sort of exfiltrate those funds off platform or to some attacker controlled address. So to talk about that, we're going to dive into our key management and sort of how it's evolved over time. Second attack scenario would be the redirection of execution layer rewards by modifying the key address parameter or validator config. So that can be done without compromising any key material, and instead be done through a source code or dependency or infrastructure level compromise. So we're going to talk about our SSDLC and see how we protect that parameter from unauthorized modification. And then the third attack vector would be the theft of validator keys. So someone that is able to gain access to the production validator infrastructure would be able to exfiltrate those keys and then demand a ransom from Coinbase at the threat of a double signing event, which would incur a significant loss of our stake principles. So we'll talk about how we prevent that. We'll dive into our infrastructure security practices and talk about some of the access controls that we have there. So let's start with the withdrawal prevention. So I'm sure most of you are familiar with the concept of hot versus cold wallets. Hot wallets are online. They are readily accessible and used to support quick liquidity and facilitate quick customer deposits and withdrawals. These use reusing the keys as they're always online. And so the benefit of that is that reusable keys are required for these withdrawal addresses, as we do frequently need to bring these keys online to support unstaking and rewards transfer type operations. Big downside of them is that they are online and always accessible, and so they're far too accessible to risk custody so much funds, $17 billion worth of that we have today. On the other hand, you have cold wallets. These are more like a safety deposit box, where the hot wallet is more like the physical wallet that you carry in your pocket. These are entirely offline, geographically distributed, and support very slow but very secure operations of funds transfers. So the big downside for the cold wallets is that the keys are technically one-time use, as once you brought a key online, it's no longer considered cold, and so that makes it not possible to use them for withdrawal addresses due to the requirement that we occasionally bring them online to support withdrawals and funds transfers. So there's got to be a better way. Introducing the warm wallet. So this is sort of a hybrid between the two. You can think of it like a safe inside your home, where funds are far less accessible than they would be in a physical wallet, but still far more accessible than they would be at the bank. So let's dive exactly into what a warm wallet is. So the pros of a warm wallet is that you can use the Shamir sequence sharing approach to create multiple distributed key shares that can be built by multiple authorized trusted parties. These can be geographically distributed. Any sort of signing for remote wallets is done on an air-gapped and secure signing device within a secure environment. And so it really creates a nice, robust system for protecting those key shares. But the downside of them is that even though these keys are never exposed to any networks or saved on disk or in another way otherwise stored outside of the memory on the device, they still do temporarily leave the memory on that single device. So there's got to be a better way yet to securely store information. So introducing multi-party computation, or MPC. This leverages our MPC infrastructure that's currently used for other CoinBase products, such as our prime and custody products for larger customers. This still uses geographically distributed key shares, cold and warm solutions that can be split amongst trusted third parties. But the true beauty of MPC is that the private keys never need to actually be fully reconstructed in memory. Each individual party is able to create a partial signature for a transaction payload, and then all those signatures can be combined at the end to produce the final signature. And this can be done without ever revealing the full form of the decrypted private key. So this is great technology. It's open source. It's been audited by multiple firms, and we've made it available on our GitHub at CoinBase/CDMPC. The other part that I'll just quickly cover is even though you have distributed key shares, you still need to make sure you're protected against your blind signing risk. And so we have a lot of features built into our MPC engine that use attestations to essentially verify at the time of signing that the payload that the user is signing is actually the payload that was intended for that transaction. So now that we've covered how we protect our withdrawal credential, we can go and talk about the next threat, which is the modification of the address and the validator config to steal the execution layer rewards. So to talk about that, we're going to dive into our SSDLC and sort of secure DevOps processes, and cover how we're going to implement that. So CoinBase SSDLC involves a ton of different technologies, but we're going to focus on three that sort of work together to provide us with secure, repeatable, and scripted builds for our stateful services. So the first one is Docker. I'm sure most of you are familiar with. It's a very popular containerization technology that provides app-level segmentation and allows multiple apps to run in the same environment and still be isolated from one another. One of the most important things with Docker is that you always need to start from a secure base image. So we at CoinBase have a custom base image that we've developed that removes a lot of the float and unnecessary functionality from sort of the native Linux bases that exist. It also includes a lot of custom functionality to support logging back to our centralized logging stack, as well as some malware analysis and heuristics that feed any sort of activity into our CISO incident response team, so we're able to make actionable decisions and solve this activity on those devices. The second technology at play here is Helen plus Terraform, so we define all of our node configuration, including the fee address and other parameters, via Helm charts. These are checked into repos. Those repos, any changes require multiple consensus from multiple different parties within CoinBase. In addition to the node config, it also allows us to store the machine config, networking configuration, really any aspect that's required to configure and deploy this node is defined there, open source, checked in, reviewed thoroughly. And we use Terraform to actually deploy that infrastructure through our CI/CD pipelines to any of our hosts that we do. Final technology at play here is GitHub. So we have a lot of integrations both with our identity providers to provide our back-level access to control who views and contributes to each of these repos. We also have custom consensus tooling that for all PRs requires consensus from multiple predefined groups so that we can ensure that multiple different parties from multiple teams have signed off on any sort of important changes to our repos. We also use a multi-stage deployment process where we first deploy everything to staging, we do some integrated and automated testing, as well as manual reviews both by our engineers and security teams for any sensitive changes, so penetration testing, and only once all of those tests are complete and reviewed and signed off on can we then deploy to production. And we have GitHub actions in place to facilitate this whole pipeline and allow us for automated deploys. And so all of these technologies work together to provide us with repeatable, scripted, and secure build and deployment for all of our critical staking services. Quick note about client diversity, which we did kind of just talk about in the last talk, but we always try to avoid supermajority clients. This is fortunately less of a problem these days, but the issue with using supermajority clients is in the event of a bug in one of them that causes a slashing penalty, the correlation factor for that slashing penalty scales up the more people are using that affected client. So we always want to make sure that we're monitoring the overall diversity within the network and ensure that we're doing our part to sort of minimize it or enhance it as much as we can. So we're currently supporting multiple consensus clients and execution clients, the Prism and Lighthouse, and again, we're never mind on red. We're always evaluating and we're trying to look for a vision where we support all of the major clients to sort of help bring that diversity even further and ideally get everything below even the 33% threshold. Another exciting technology that we use here is a custom load balancer, which is based on the high availability proxy, which is an open source tool. We have this work in conjunction with our readiness probes for our node containers, and so there's a custom script that essentially checks each node for number of peers to ensure that's adequate, and checks whether or not that node is in sync, and is at a correct block height compared to the others. And then that load balancer takes all that data and redirects the validated client traffic to the best available node pair. All that helps ensure that our nodes are always available and that they're able to submit attestations and proposals in a timely manner. So let's talk about monitoring now. There's basically two tools in scope for this. First one is Exegate, which is a smart contract monitoring service that allows us to define lots of custom heuristics to track anonymous function calls, as well as any sort of balance discrepancies, transaction or contract call reversions, and a lot more. So the two main contracts that are in scope for this are the baking contract from Ethereum, as well as the cash deposit contract that CoinBase has developed to fund our validators in bulk. On the centralized monitoring side, we have Datadog. We have custom telemetry that feeds all of the node logs and metrics from each of our consensus execution and validator nodes up to Datadog, and then that enables us to create a lot of dashboards tracking both how the host is performing in terms of CPU and memory utilization, as well as the peer count for each of these individual nodes, the sync status, and a lot more. We also have staking performance dashboards, which allow us to monitor for slashing events, which as you can see there, there are none, unfortunately. And then as well as attestation and proposal correctness and times. We also have a lot of dashboards to track the individual performance of each of the live relays that we support, so we can ensure that we are always redirecting traffic to the best available relay, providing ultimately the best rewards back to our customers. There's a whole lot more monitoring that we do. It's just a snapshot of it, but hopefully that gives you a glimpse into some of the things that we care about and want to track for this infrastructure. So now we've covered the first two threats of withdrawal address credential tampering and modification of the fee address. We can then move on to the third one, which is preventing someone from accessing the production environment and exfiltrating our validator keys. So to talk about that, we're going to dive into our infrastructure security and talk about some of the access controls that we implement there. So access to the staking environment is very tightly controlled. As you can see there, the external actor first goes right through all of our enterprise security controls. This includes various SSO solutions, as well as gaining access to the VPN, circumventing numerous device restrictions, and able to do all of that while circumventing the constant eyes of our CSIRT incident response teams. So on the internal side, the internal threat actor is able to circumvent a lot of those controls by being an internal actor, but they still have a lot of other controls, such as just-in-time access. So access to the staking environment is only provisioned for a short amount of time necessary to perform whatever duty is expected to be performed. They have to provide clear documentation on why they're accessing the environment and what exactly they need access to. That requires multiple approvers from multiple different groups within CoinBase, and then even then they're only able to access a certain subset of our validator infrastructure. So that sort of guarantees that no one for any reason is able to gain access to the entire set of validators at any given time. We have consensus, like I talked about, for both the approval team of the environments and any sort of other access that we needed. Also, CoinBase have. There's also resource isolation, so we keep our staking infrastructure entirely separate from any other services that may be in CoinBase to prevent the opportunity for lateral movement and minimize the blast radius. And if some other service becomes compromised, there's no direct path to access the actual staking infrastructure. There's also separation of duties, so the teams that are responsible for the operations of this infrastructure are different than the teams that are responsible for approving it, and so that prevents any sort of self-service approval type scenarios where someone's able to grant themselves access to something. It helps minimize the chances of a single individual or even a single team from gaining access to the entire system. And so all of this works together to provide a defense in depth approach and minimize blast radius in the event of this requirements. So we've talked a lot about some of the internal measures that we're implementing to secure this infrastructure, but how can we externalize that vision and demonstrate the effectiveness of these controls to our customers and to the broader community? So let's talk about that. So we've recently partnered with the Blockchain Security Standards Council to help co-author the Node Operator Standard. It's essentially 32 different controls designed for secure node operations. There's 5 domains here this covers. The first is protocol onboarding. So how do we select and understand the security and operational properties of any of the protocols we support? There's also the network participation aspect where we need to understand what our role as the node operator is within the broader network and ensure that we're able to meet all of those duties to promote the health of the networks that we're supporting. Resilience and performance. So how do we design and build our infrastructure in a way that is both resilient to network level spikes and performant enough to meet both the operational needs of the network as well as the operational load put on nodes by the backend services that need to interact with them. Security and access controls, that's a lot of the stuff we just talked about, with ensuring that access to your environment is possible in terms of emergency, but still restricting it so that unauthorized parties cannot easily infiltrate it and prosper. Final domain is the transparency. So how do we behave as an ethical actor within the network and ensure that we are doing our part to promote the health and longevity of any of the networks that we're supporting. And so we're currently evaluating our staking infrastructure against this standard to ensure that we both meet and ideally exceed the standards that we've helped define here. This is a great standard. I think it's very comprehensive but flexible enough to apply to both large-scale institutions, node providers as a service, up to the hobbyists that's looking to just run a single node at home for fun, just to figure it out. And then we're also sort of working with third-party auditors and providers to help encourage them to offer this as a service so that CoinBase and other entities can get a certification against the standard that helps externalize a lot of the hard work that they've been doing to secure their nodes. So yeah, thank you all for joining and listening. We appreciate it.